So let's do a couple of application problems. I'm given a revenue function that's in billions of dollars. It's for Procter & Gamble, and it's for the years 2010 through 2015, where x equals 10 is year 2010. So we're asked to find where this has a local maximum, so we know we need a derivative. So the derivative is going to be negative 2.2x plus 27. And I want to set that equal to 0. So negative 2.2x equals negative 27, and divide by negative 2.2. And we're going to get that x is about 12.3. So this is not enough to declare that it's a max. All you know is that the derivative is 0 here. So x values, let's see, we have 10 is where this function begins to be valid, and then 15 is where it stops being valid, and then 12.3 is the point we have found where the derivative is 0. So now we need to check the derivative in the first interval. So let's check r prime of 10. Negative 2.2 times 10 plus 27, and that's going to be positive. And then let's check r prime of 15. And that's going to be negative. So now we can see that the revenue function goes up, and then it reaches a high point, and then it goes down. So this is a local max. And it's happening when x is about 12.3. So when x is about 12.3, that's the year 2012. So our answer would be during the year 2012 was when they had a local maximum of revenue. Okay, then this next example is a cost function for Southwest Airlines. And we're being asked to find all local extrema. So we need to find the derivative, and it's going to be negative 0.324x squared plus 7x minus 36. And I want to know when that's 0. Well, that's pretty ugly, but we are algebra professionals, and we have a tool that helps us find the solution of a quadratic formula. Oh yeah, it's the quadratic formula. So I'm going to have the opposite of 7 plus or minus the square root of 7 squared minus 4 times the a times the c all over 2a. And if you find those two values, you're going to find it's about 8.4 and about 13.2. So you get two answers, one with the plus and one with the minus, and those are your two results. So then we need to put those on a number line, and this function is only good starting at 7, and then we've found 8.4 is a critical number, and 13.2 is a critical number, and 15 is the end of when this function is good. So these are x values. And then I want to look at the derivative, and I know the derivative is 0 at 8.4, and it's 0 at 13.2. So now I need to figure out what happens in the intervals. So I'm going to do c prime of 7, and that's negative 2.876. So I'm going to put 7 into this c prime function. So I get a negative number here. And then when I do c prime of, say, 10, And I could do any number that's in between 8.4 and 13.2. So I pick 10 because it's easy. And I get 1.6, so that's positive. And then I'm going to do C prime of 15, and I'm going to get negative 3.9, so that's negative. So now we know what's happening with C is it's going down, and then up, and then down. So we know we have a local min and a local max. So the locations of the extreme values when x is about 8.4, C has a local min. When x is about 13.2, C has a local max. And then we're also asked to find the value of the function at each extreme. So you'd want to find C of 8.4. And I got about $3.05 billion. So make sure you're plugging back into the C function. And then C of 13.2 was about $8.74 billion. And that's it for section 12.1.